Today I would like to present my research paper on investigation of electric vehicle, EV and renewable energy sources for low voltage distribution network in Malaysia. So I will talk about the introduction first. So since we know now the global climate change has been a major issue in recent years, one of the largest carbon dioxide emission is the transportation sector, as it mainly rely on the use of fossil fuel. Evidence shows that approximately 20% of energy usage worldwide is from the transportation sector, and about 25% of the usage contributes to the global carbon emissions. Nearly half of these emissions can be attributed to passenger vehicles. So to reduce this carbon emission from transportation, so electric vehicle or EV can be replaced with fossil fuel vehicle. So EV it emits around 50 grams of carbon dioxide per kilometer, compared to fuel cars currently emit approximately 100 to 150 grams per kilometer of carbon dioxide. So another study also shows that EV has 2.5 tons of carbon dioxide emission, and it can be reduced annually, but instead of this advantage, there are challenges to be faced when we want to implement electric vehicle cars in Malaysia. So in this research also, I will talk about what is the challenges and what to overcome. So the problem is the sudden increase of EV charging station could have an effect on the power grid. It will impact the voltage profile, the power losses, peak demand, and transformer loading. And then from the literature, another study also shows that or suggests that high implementation of EV infrastructure will increase the demand to the distribution network and will cause overloading. This research will focus on modeling distribution network to analyze the characteristic of the low voltage distribution and also examine the impact of integrated EVs into a low voltage distribution network. So the objective for this paper is to model a typical Malaysia's low voltage distribution network with renewable energy and study the effect of implementing ultra low carbon emission EVs in different parts of the network by using the PSCAD and also MATLAB Simulink. The model is validated to show that EV charging station with distributed generated units facilitates the connection and improve the stability of the system by keeping all the bus bar within the acceptable operating limits. So now I'm going to talk about the methodology. So this is the EV load modeling that will be connected to the low voltage distribution network model, which in turn will be connected to the modeling of the renewable energy system. The low voltage distribution network model used in this project is the actual distribution network located in Taman Impian Putra, Port Dickson, Malaysia. So the incoming voltage level for the transmission system is 11 kilovolt, and the voltage supplied to the consumer is 415 volts, three phase. So this system uses a transformer which is step down the voltage from 11 kilovolt to 415. And there are two transformers in the system. Okay, and this transformer, the two transformers in the system which are rated 500 kilovolt and also 750 kVA. Sorry, 500 kVA and 750 kVA respectively. And the connection is delta Y connection. The 500 kVA transformer has three feeders, okay, and the 750 transformer has four feeders. You can see here, this is three feeders, ABC, and four feeders. So the total number of feeders in this system is seven feeders. The number of feeder and type of consumer of each feeder is shown in this figure. So this diagram, okay, firstly, the typical load demand throughout the day for 24 hours is obtained from the literature. So as shown in this figure that at the table, okay, the demand curve where one represents the maximum, this one represents the maximum demand from 7 p.m. until 7 p.m. Okay, and then 0.27 somewhere around here. 0.27 is the minimum demand of the day at 8 a.m. So that means 7 p.m. is the maximum demand. Most people will charge their EV cars at 7 p.m. and minimum demand is around 8 a.m. So the actual demand in kilowatt can be determined by multiplying the maximum load demand to the normalized demand, and the respective time slot. So this table shows the data extracted from PNB handbook. It shows that different type of premises have different type of premises will have different maximum diversity demand. So the maximum diversity demand is the urban area, whereby for single story terrace, double story terrace, double story semi-detached, and also double story bungalow is used accordingly to the number of types, as you can see from the table. So this is for different type of consumers. So the EV model chosen for this study is Nissan Leaf, which has battery capacity of 24 kilowatt per hour and 3.3 kilowatt on board charger. So the reason for choosing this model is that it has the largest battery capacity compared to other EVs that launch in Malaysia. The customer in this network is assumed to use the level 2 charger, which operate at 208 to 240 volt, single phase with a maximum current of 32 ampere maximum. So this is the charging scenario. So in order to maximize the battery life, the state of charge of EV is maintained between 20% to 80%. So in this scenario, the plug-in time is uncontrolled. Another assumption that made for this project is EV are being plugged into charger as soon as the customer return to their home after work. So typically in Malaysia, work ends in Malaysia around 5:30 p.m. to 6:30 p.m. So considering the traffic density of Malaysia, it might take up to 30 minutes to 1 hour, 30 minutes for the customer to return home. So it's assumed that the EV plug-in time of around 6 p.m. to 8 p.m. So it requires at least 4 hours to fully charge the car. So thus the EV load will be plugged into 6 p.m. to 12 p.m. around that. Okay. So I take the average, the maximum demand around 6 p.m. to 12 p.m. So the EV loads will be connected to the network during peak hours. So the peak hours of maximum demand is assumed as 7 p.m. So the simulation, everything is done within this maximum demand. The penetration rate of EV modeling varies from 0 to 100% with 20% of increment. So the penetration level indicates that how many customers have one EV in the figure. Solar energy is used as a renewable energy because the location of the distribution network, which is located in the residential area. So there is also problem on the implementation of solar energy into the distribution network with EV. So as I mentioned earlier, the EV load charging time is modeled at a peak demand of 7 p.m. to 11 p.m. But during this time, the solar irradiation is very limited. So solar system with energy storage are proposed in this research. So for the results, okay, I will go the results before we integrate the EV and after we integrate the EV. So before we integrate the EV, the result shows the behavior of the distribution network at these two graphs. Okay, so one is for the transformer 500 kVA, another one for the transformer 750 kVA. So according to the findings, the transformer demand exceeded the transformer limit during the peak hours. You can see here, okay, extended the limit and remain acceptable limit during the off-peak hours. And then we also check the voltage profile. So the graph shows the maximum voltage sagging of the 500 and 700 kVA transformer during the peak hours drop to 412 volt, which occurs at 7 p.m. Okay, the voltage supposed to be 415, the three-phase voltage. But during the peak hours, the voltage dropped to 412, especially at 7 p.m. So on the other hand, the voltage level during off-peak hours dropped. Yeah? So the result shows the voltage of the transformer is maintained within, even though it dropped 412, but it is still maintained in TNB acceptable limit set because TNB limit is 6% voltage drop. So it's still under limitation of TNB. But after we integrate with EV, what we can see is this graph shows the load demand of 500 kVA transformer for EV penetration rate 0 to 100%. So compared to the base load, the transformer load for 100% penetration rate has increased. So the right figure here shows the relationship between the voltage sag and also the EV penetration rate from 0 to 100. So the voltage level from 0 to 100% penetration rate maximum is 406.8. And the percentage sagging is around 1.98%. And then for 550 kVA transformer, it's similar also. We compare to the base load and we use the 100% penetration rate. And it increased about 40%. So the voltage level from 0 to 100%, the penetration rate maximum is 400.5 volts, and the percentage voltage sag is minus 3.49%. So from this result, the distribution network after the EV integration with renewable energy are analyzed. And the table here shows that the result after the integration of renewable energy system, we model the transformer working around 70% of the load, 70% load. Okay. So the loading level of voltage sag is the same as at peak hours, regardless of the penetration rate. So the result shows that loading of the 500 kVA transformer and 700 kVA transformer is 70%. Both also showing the same. Okay, the voltage sag for 500 kVA is 700 is minus 1.2%, voltage set, and for 700 kVA transformer is minus 1.81. So this shows that the stability of the system is restored after the integration of renewable energy in this distribution network. So to confirm this, we validate the renewable energy model. So this table shows the input parameter into the Simulink. We validate it by using MATLAB, okay, for 100% penetration rate for 500 kVA transformer and also 750 kVA transformer. So from the validation, we got the figure shows the time taken for the battery in the renewable energy system for 500 kVA transformer is fully charged will take 4.06 hours. And the time taken for the battery in the renewable energy system for 750 kVA transformer to fully charge is around 3.81 hours. So from all these results that we get, okay, we make a conclusion of the discussion, make it in this table. So the table, this table shows the data for both transformer before the integration of EV. The result shows that the system for both transformer is heavily loading during peak hours, underutilized during off-peak hours. So this is not efficient, okay, because this is not really efficient because most of the equipment in the distribution network is not fully utilized during the off-peak hours and only operate in a short period of time during the peak hours. So smart grid system with real-time traffic system can be implemented to reduce the peak demand. So for the price of the tariff could be more expensive during the peak hours and it will be cheaper during the off-peak hours. So this will discourage the consumer to use power during the peak energy time. So we can implement this. Okay? And then the result in this table shows the impact of EV to the distribution network. So the result shows that the higher the penetration rate, the higher the voltage will set. You can see from here, 0 to 100%, higher the penetration, higher the voltage set. So, and the loading of the transformer. So, increase in EV load to the distribution network reduce the voltage of the transformer on the distribution network. So although the result shows that the voltage stack for all the penetration rates are within the voltage stack limit from TND, because TND limitation is minus 6%, the voltage rate of change of the voltage is still drastic between the peak and also the off-peak, which could lead to blackout in the distribution network. So renewable energy system is still required to maintain the stability of the system and also to overcome the unexpected changes. So as a conclusion, okay, from the result shows can suggest a suggestion is to implement smart grid system into the distribution network, which is able to effectively estimate, predict, and reduce the load demand in the distribution network. So, for instance, using smart meters, smart EV charger, real-time tariff system can be implemented into the distribution network to reduce the effect of EV charging without the investment or large scale of renewable system. And then also research or development regarding integrated of smart grid into the distribution network with EV load can be conducted in future. This is the PS-CAD simulation model, this one to show, and this is the overall renewable energy system model in MATLAB simulation. Run this program. So I think that's all. Any questions? No question, I will end my presentation. Thank you so much.
Hello, good morning. Can you hear me?
Yes, can.
Okay, so I will start with my research seminar presentation. Uh, Hi, good morning, everyone. I'm Hasalli binti Ibrahim from School of Engineering. I will be presenting my research topic, which is an investigation into the technical feasibility of incorporating wind energy for electrical vehicle charging system. So this is my presentation outline. I will talk a little bit about the EV system, the problem, objective, scope, a little bit theoretical parts, methodology, data and discussions, and ending with the conclusions and recommendation. Okay, about 25% of the global carbon dioxide is produced by the fuels, which is they come from the conventional internal combustion engine system. So in nowadays, they have a lot of electrical vehicles has been produced, and they have four types of electrical vehicles, which is battery electric vehicles. This is a common and the most used in the automotive industry, the hybrid electric vehicles, plug-in hybrid electric vehicles, and the fuel cell electric vehicles. So for the BEV, all the electrical vehicles has been powered by the batteries, and there are no internal combustion engines that use the fuel has been attached to the vehicles. So this BEV has been include the electricity grid, and they use a regenerative braking system in their system. So for the HEV, there are combination in between of the battery and the fuel that used in the vehicles, where they will be recharged by using the braking system, where they also use the regenerative braking system. And there are no external charge port compared to the battery electric vehicles, where they cannot be charged from the electricity grid. And for the plug-in hybrid electric vehicles, these types of vehicles, they have both electric battery and also the IC engine system, where they have electricity grid and the port to supply the electricity to the cars, and also they can regenerate the power from the braking system. And for the fuel cell electric vehicle, this one is slightly different because they use a fuel cell vehicles that employ the fuel cell technology into their system, where the fuel cell will be used to generate the electricity in the vehicles, where this fuel cell is related to the chemical energy and converted into electric energy. Okay, why we study about this thing is because of usually when we want to recharge the battery, they will take a long time, and they will take they will have several types of charger system, and some charger uh can do a fast charging, and some of it they just do a slow charging. And the fastest charger, they will take almost 2 hours to fully the battery. And last time they have lack of charging station, but nowadays they have improvised. We can see more charging stations has been provided, especially in the highway area. And the objective of this research is to select a suitable full small-scale wind turbine that will be implemented into the EV battery charging system to generate the kinetic energy, and this kinetic energy will be converting to the to the electrical energy. So to validate the use of wind turbine, we will build the prototype and test their performance to measure how much voltage output that can be produced for one cycle. So for the scope and the limitation, the wind turbine will be designed to harvest the energy and to recharge the EV's battery pack. And it will start with the designing a 3D model by using a SolidWorks. And this 3D model will be printed out by using a 3D printer. And we will be testing the prototype by using a wind tunnel. So this wind tunnel we use to provide the air velocity to the prototype, and from there we will attach the multimeter to measure the voltage the output voltage that can be come out from the wind turbine. And there are not much research related to this study, so that we are more the study is more towards to the theoretical study. So about the literature review, what we focus is in terms of what types of energy source that can be produced or can be supplied to the EV system, where we can have come from the battery, come from the fuel, and also they can have in the form of specific energy, where this specific energy is very important to give a total power to the EV system. And then we also need to identify the types of suitable battery that can be used, such as the lead acid, nickel metal hydride, and also the lithium ion. So all of these battery, they have a pro and cons, where lead acid is usually they are more cheaper compared to the lithium ion. And for the nickel metal hydride, they are more recyclable. Okay, means that the battery can be recycled. The same goes to the lithium ion. And for the charging system, we can use two types. Either they are alternating current or direct current. So this is two types of charging system that can be implemented into the EV system. And also we study about the wind turbine, especially in terms of the types of the wind turbine. Either we can use the horizontal axis wind turbine or the vertical axis wind turbine. So from the study, we see that the VAWT or vertical axis wind turbine is more suitable to be implemented into the system because of they are suitable to be used for the small application in the small design, in the small scale, and also they can be the area that they are covered is not too large, so that they can easy to be compacting into the system. And also we will involve in terms of the airfoil parameter or the airfoil standard, which is they are related to the blade system of the wind turbine, where this is important to give the lift to drag force performance, to know how much performance they can provide to the wind turbine. So we use the NACA 4415 for these types of wind turbine that will be implemented into the EV system. Okay, so at the first thing in our research, we will start by selecting a suitable component that will be implemented into the EV system, which is the wind turbine, where this wind turbine will be put into the in the parts of the vehicles that will link directly to the battery system. So this is another is considered as a renewable energy resources that will be directly implemented into the EV system. So we will study about the wind turbine first. So to study about this, we will look at the blade. So the blade system, we make a comparison between NACA standard and NREL standard. So after the study, NACA is more suitable to be implemented at the high Reynolds number, where when the air velocity is turbulent flow under the turbulent flow characteristic, compared to the NREL. So as you can see in the graph here, okay, the patterns of the NACA standard is higher performance compared to the NREL standard, which is this one is related to the ratio of the coefficient lift to drag force in order to measure the performance of the blade system, which is they will link to the airfoil parameter. So the vertical axis wind turbine is also implemented, okay, where they are suitable to be used for the small applications and they are less complicated compared to the horizontal axis wind turbine. And other than that, we also use a permanent magnet to give to generate the electricity to the wind turbine. Okay, so this is a design, the model, where from a different view, side view and the top view. So this one, after the design, we will print out using a 3D printer. So we have a horizontal area, which is the entrance is the horizontal inlet where will be attached to the turbine. So in this study, we also have two different study, okay, where when we implement a nozzle into the design and without nozzle, okay. So we have a two different result where the design with the nozzle and the design without the nozzle. So the model will be put under the car. As you can see in the red highlighted area is the part where this entrance will be placing. So there will be in uh the exit part where they will directly go to the battery pack area, and the turbine will be put inside the this system. So for the wind turbine will be designed like this. So the left side is a wind turbine model and the right side is a nozzle that will be attached to the system. So we use the subsonic wind tunnel to analyze the air performance, especially to know the lift force and the drag force. That and also one more thing is the current. Okay, the current that can be produced by this wind turbine. So this current we will do the analysis in order to know how much speed that they can at what speed that this current can be produced in order to supply to the battery. So the turbine with the motor, we connected to the multimeter and placing inside the wind tunnel. So we do the several range of speed, start from 1.82 up to 11.14 meter per second. So you can see the range of the speed is very low. So since that this is only the prototype, a small scale of system, and even our wind tunnel is only a subsonic. So subsonic is under low air flow measurement. Because for the air we have several types: subsonic, sonic, and supersonic. So for the subsonic is under a low for performance. So that's why the speed range that can be measured is also low, so that the testing or the output result that we get also is low compared to the actual, and but it's still comparable because of we do a small scale of prototype. So the voltage is being recorded using the multimeter. So this is the experiment setup inside the wind turbine, inside the wind tunnel, okay, where the wind turbine has been placing in the work area, and the multimeter has been attached directly to the wind turbine to measure the current. And also this diagram is without the nozzle. So there we have a different result between the with nozzle and without nozzle. So this is a result where we have the attachment of nozzle and without the nozzle. So as you can see, with the nozzle, they can produce higher velocity compared to the without nozzle at the constant velocity. So the voltage can go up to 370 millivolt without the nozzle, and also 407 millivolt with the nozzle, where they are increased by 10%. So this means that the use or the implemented of nozzle is able to increase the velocity in the wind turbine system. And this is all the design parameter that we measure based, and then we do the comparison between the theoretical and the design. So based on the calculated parameter, okay, we used to do the design, okay, such like the tip speed ratio, the swept area, and the solidity. All these value we use to measure uh, uh, the the air density and the wind density. So all this is a parameter we use in between of the design parameter and also the calculated parameter. And not only from a theoretical calculation, we also make a comparison between another researcher to see the validity of the result that we get. So here is a comparison between the prototype and also from other researcher that we get from Quartis paper. So you can see here the Quartis result is higher than our prototype. This is because of their model or their prototype is higher than us. But if you can see the trend of the graph is similar. Okay, so it means that they can be validate that our result is in the good way. Okay, so as a conclusion, because of this is a feasibility study, so it show that the implemented of the wind energy with the support of the wind turbine in the system is able to provide a renewable energy to the EV system in order to reduce means that they can conserve own energy supply to the EV and energy other than we use the electricity, and this is a more suitable if let's say the area of the charging system is quite far from one point to another point. So in order to meet uh, the next charging system, so they can reuse their own supply energy that come from the wind energy. So from the result, we can say that if they have low speed, means they can produce low power. So we need higher speed to give a more power to the system. And the implementation of the nozzle is able to increase the amount of air velocity into the turbine system and generate more power. And also the cord length to the airfoil parameter is important to give better air performance and also stability. So we need to have more large cord length to have better stability and better lift to drag force performance. So that's all from my side. Any question? Okay, thank you everyone.
Hi everyone. Can you guys hear me? Hi. Good morning, everyone. I'm Desmond. Today I'm going to present my research paper exploring the global hydroponic cultivation system, current and future perspective. My main supervisor is Mr. Chua and Chua Huang, and co-supervisor Dr. Go Teng Teng. Both of them are from University of Wollongong. And also an external supervisor, Dr. Wei Jiang from University of Nottingham. First of all, the climate around the world are changing day by day. According to the climate downscaling study, the temperature in Malaysia will increase by 3 to 5 degrees Celsius by end of the 21st century. The climate change are affecting plant growth and plant production around the world. The plant that require a low temperature couldn't withstand the heat stress and causes in reducing its development. The change in temperature is affecting the rate of plant development and causing the plant yield to reduce by 80% compared to a normal temperature. So, how is the weather affecting the crop's production? This is the illustration of how the plant function to respond the carbon intake. The influence of weather disaster will affect the crop production. Under a dry condition, the crop will close their stomata and limit the evaporation water loss. By doing so, it will reduce the carbon uptake while in photosynthesis stage and reducing the yield output. The hydroponic market are growing rapidly in recent years as we could start seeing people start planting in many places. The actual global hydroponic market size in the US was valued at USD 18.52 billion in 2022 and is projected to grow at a compound annual growth rate at 12.8% from 2023 to 2030. This high growth rate is attributed to the increasing of hydroponic system for using for indoor farming of vegetable. Based on the hydroponic type, the market is segmented into aggregate system and liquid system. The aggregate system segment accounted for the largest revenue share of 53.4% in 2022 because it is widespread among indoor hydroponic farmer due to easy setup and inexpensiveness. However, the liquid system segment is estimated to register as the fastest compound annual growth rate of 15.9 over the forecast period, and it is increasing popularity of closed system cultivation among the farmer. The deep water culture and nutrient firm technique system are both increasingly used to cultivate lettuce and other leafy vegetables. Vegetable is still an important industry among other in Malaysia, as this industry has a bright future as demand from both domestic and global consumer increase every year. The increased prevalence of health concern and evolving lifestyle has resulted in increasing of consumer demand on vegetable, particularly those that are produced with minimal chemical input or are classified as organic. In the year 2015, Malaysia vegetable production has a rise of around 58% in comparison to the data from 2010 and amounted to around 1.03 million metric ton. However, the production is still insufficient to meet the demand of local consumer. The demand for vegetable had notable growth, rising from 1.58 million tons in 2010 to over 1.91 million tons in 2015. The increased scarcity in supply can attribute to the heightened consumer demand for vegetable. China, Netherlands, USA, and Thailand are the source of around 880,000 tons of vegetable imports to Malaysia. The conventional farming method of agricultural cultivation has traditionally referred to the practice of growing crops in open-air field, utilizing irrigation technique and actively supplying nutrients to the plant. The conventional farming has slower growth rate and less consistency compared to hydroponic farming. The nutrient level are depending on the soil, unlike hydroponic farming where the farmer could just adjust the nutrition level by using nutrient solution. The conventional farming are also based on seasonal, so the product will be stored or processed, which is affecting the price instability. Unlike hydroponic farming, the production are available around year-round. The products are fresh and healthy, hence the price are more stable. In hydroponic system, there are various types of category available in the market. The deep water culture, deep irrigation, aeroponic system, nutrient farm technique, ebb and flow system, and lastly, the aquaponic system. All these different systems has its own advantage and disadvantage. The farmer has to choose the right system based on the type of plant growth. A deep water culture system is suitable for both small scale and large scale production. This system is working with the larger plant because it will be able to provision the water where it could supply the nutrient directly to the root of the plant. However, because the nutrient solution is exposed to elements that will dilute the pH and EC solution, hence a high-performance monitoring system is required to monitor the in and out flow of the reservoir. It also requires high water usage, which may not be efficient compared to other systems. A deep irrigation system is only suitable for small-scale production, because it will provide each individual plant root with an appropriate amount of nutrient solution. The extra nutrient solution can also be collected and recirculated within the system to recycle the nutrient, but it will cause more fluctuation in the pH and EC value. Aeroponic systems are designed to be complete automation system. This system is the most water saving, and it is about 90% water saving compared to conventional farming. The roots are exposed to the air so that they will always have enough oxygen for the crops. Aeroponic is suitable to grow both small and large scale production plant, but it is highly consumable where it could take up more vitamins and minerals to make the plant more nutritious. So it requires a higher maintenance cost and more monitoring of the system. The nutrient film is a technique that can be built both horizontally and vertically. It is built with long and small width PVC tube and that recycle the nutrient solution and feed the nutrient to the plant in a consistent amount. This system also minimizes the space used and maximize the air for the roots. Even so, this kind of system is not suitable for large plant, and the water will heat up on hot day because the recycling water will be trapped in the tubes. Ebb and flow system are more beneficial to water-growing plant because they will flood the root with nutrient and let them flow to the other end to recirculate. This system requires low supervision and maintenance. Anyhow, this system will be challenging as it will be hard to keep the nutrient level consistent and it is not suitable for large-scale plant. Lastly, the aquaponics are efficient, sustainable, and high productivity compared to the other hydroponic system. It also uses 80% less water to grow 8 times more yield compared to traditional farming. This system provides natural fertilizer from fish waste and organic fertilizer. However, this system need to maintain 2 different temperatures which are determined by the fish and the crops that have been chosen. So this system is requiring high consumption of electricity and needed a professional handler to maintain. The available of crops is also limited in aquaponic system. The traditional farming system has remained unchanged since the beginning, and there have been improvement and enhancement to the genetic irrigation and seed in the farming process. However, the step of planting the seed and growing the system remain unchanged, which is hard to maintain while having different seasons. Hydroponic systems are introducing a significant number of advantages over the traditional farming system. The most important parameter on the plant is the water. A hydroponic system can minimize the water usage on every plant and help to save water throughout the whole farming process. Other than that, in hydroponic system, the most important parameter in growing the plant can be controlled throughout the growing process. Example like pH control, EC control, temperature control, and nutrient solution control. This control can help to minimize the irregular production and maximize the plant yield with healthier outcome. According to the studies, hydroponic has more advantages than traditional land-based farming. There are quite a number of researchers working in hydroponic studies. However, most of the researchers focus on pH, EC, environmental temperature, and other parameters. According to the findings of this study, many hydroponic growers are increasingly focused on the crop's quality improvement. The data that is available on the roots temperature study of the hydroponic system is lacking. As a result, the optimization and improvement of growth parameter should include both productivity and quality. With the current situation, in the world climate change and increasing of population, the hydroponic system could help to improve in vegetable production. There are 3 areas must be prioritized in order to increase agriculture output. By using the most space-saving system, hydroponic system, it could help to reduce the space used to produce more crops within the same area used by the conventional farming. The current hydroponic system has optimized space use by implementing a vertical farming system, which show the result efficiently. Secondly, a system with a temperature of 24 Celsius has shown significantly higher yield production compared to 25 degrees Celsius, 26 degrees Celsius, and 27 degrees Celsius water temperature with leafy vegetable. Lastly, there are also numerous studies that have tested the result of controlling the water quality and show great result in producing higher yield. However, there is a lack of study examining the impact of water temperature on plant growth in hydroponic system. Every plant that need a different water temperature in order to grow healthily. The precise water temperature fit to the hydroponic system would help to rapid the plant growth. Hence, I would like to recommend more researchers work on the water temperature studies to improve the hydroponic production. That's all for my presentation. Thank you. Any question?
Okay, Assalamualaikum and very good morning. Can you all hear me?
Waalaikumsalam. Boleh.
All right, okay. Okay, so today I would like to, Today I would like to present my research paper on effect of strain rate and flexural behavior of unidirectional carbon fiber reinforced polymer composite. This is the experimental investigation and also finite element analysis. Carbon fiber reinforced polymer composite materials has a highest strength to stiffness. According to the previous research, it is from the previous research, it is found that there are 2 factors that actually influence the quality of carbon fiber reinforced polymer, which is the carbon fiber layout and also carbon fiber to polymer ratio. So strain energy analysis actually gives the data regarding the speed at which the material is deformed and the lasting effect of the material. So this research investigates the influence of the strain rate on the flexural behavior of unidirectional carbon fiber reinforced polymer composite. So the composite is actually a fabric type, as you can see in the picture. So it is oriented in a single direction. That's why we call it as a unidirectional CFRP or carbon fiber reinforced polymer. This offers the high stiffness and strength in that direction. So the lack of research on unidirectional carbon fiber reinforced polymer material under different strain rates actually represent the significant gap in understanding the material's flexural behavior. So in this study, we will try to see or fill the gap and see what are the significant difference on the material flexural behavior when we give the different strain rates to it. So therefore, this study aimed to address this gap and provide insight into how unidirectional carbon fiber reinforced polymer material behave when subjected to different strain rates. So the material that we use is the unidirectional carbon fiber reinforced polymer fabric. We also use epoxy laminating resin and also epoxy laminating hardener to harden the material. The sample thickness we use, there are two different thickness we use in this experiment, which is 3 mm and 4 mm. The thickness of this carbon fiber reinforced polymer was calculated based on the impact of the resin infusion. The standard we use is ASTM standard. ASTM stands for American Society of Testing and Material. So this standard we use D790. This is for the flexural testing. And the sample size for both, we are using the same length and width, which is 130 mm and 13 mm. But the thickness is different, 3 mm thickness and 4 mm thickness. The strain rates we use is from the range of 5 to 25 mm per minute by incremental of 5 mm each. So we have 5 different strain rates that we use in this experiment. So for the experiment, the specimen were fabricated using a hand layup method involving the manual placement of unidirectional fabric layers onto a mold and resin impregnation using a brush, as you can see in this first picture here. And the testing, we use the flexural test is conducted. So this is the specimen. This is the specimen for the two thickness, 4 mm and also 3 mm. And this is the testing that we did. Flexural test was conducted on the composite specimen to determine the maximum load, maximum stress, and also flexural modulus of the sample. And we also did a finite element analysis simulation to see the maximum load and also maximum stress when we give the same load on the specimen. From the results, we can see that this is the result, actually shows the total results for the strain rate for different strain rates for two different thickness, 3 mm and 4 mm, and also the maximum load, stress, flexural modulus. So these are for the experimental, and the others here, this one is for the finite element analysis. And this is the errors that we see between the experiment and also the finite element analysis. So from this graph here, you can see that the same thickness does not actually give any significant difference in the maximum load and maximum stress value. However, there is a significant increase in the value when the thickness is changed from 3 mm to 4 mm for the carbon fiber reinforced polymer samples. So as the conclusion, okay, what we did is we take the average for thickness 3 and 4, and then we tabulate this data. And what we can see here, we can see that this is actually the comparison between the experimental and simulation result for the material with different thickness. Okay, the result focus on maximum load and also the stress value to evaluate the correlation between the experimental finding and also the finite element finding. So what we can see is from the experimental, the maximum load, the experimental average percentage is lower by 0.65. The negative sign here shows it's lower compared to the simulation result. And the maximum stress from the experimental shows the percentage is higher. In terms of maximum stress, the experimental is higher by 0.6% compared to the simulation results. So from here, what we can see is the maximum load and also the maximum stress average increase for experimental is 104 and 105%, which compared to the finite element analysis, which is 110 and 103%. So an average of 2 to 7% increase of flexural modulus was determined by increasing the carbon fiber reinforced polymer sample thickness by 1 mm. When we use the different strain rate varies from 5 mm per minute to 25 mm per minute. From the graph here, this is actually the flexural test results that we get. So from the graph here, we can see the 4 mm thickness samples generally withstand higher stresses at lower strain compared to the 3 mm thickness sample. This suggests that the increased thickness enhances the material ability to bear stress before failure. And also we can see here for the highest strain rate, which is 25 mm per minute, the peak stress does not show any significant increase because this is the saturation point in the material response to strain rate increase. So from the results, okay, the observation that we get is there is no correlation were discovered with the increasing of strain rate and the flexural strain within the same thickness. However, there is a significant decrease of maximum flexural strain of the sample when the thickness was changed from the thickness was increased to 4 mm compared to 3 mm. So the conclusion that we can do here is the varying the strain rate did not cause any difference in results obtained when the carbon fiber reinforced polymer dimensions were constant. However, increasing the thickness of carbon fiber reinforced polymer increased the maximum load and also maximum stress and flexural modulus values while reducing in flexural strain. So the recommendation, we can give one recommendation here for future study, where is increase the strain rate variation to a much higher strain rate might likely show some results. And also another recommendation that we can give here is to develop further with more thickness variation on the carbon fiber reinforced polymer samples. That's all from me. Thank you. Any questions? Okay, if no questions, then I'll stop here. Thank you very much.
Okay, good morning, everyone. Actually, this section, this topic is required present by me, but Ahmad Omar is also one of the team member, so he will present on behalf of me.
Good morning, everybody. I'm trying to share the screen. Just 1 minute. Everyone can see the screen now?
Yes, we can see the screen.
All right. Thank you very much. Good morning again, everybody. Today I'm going to present a research paper about performance analysis of wireless power charging and future enhancement techniques for drones. This paper, the research work was supervised by Prof. Yep from Sunway University and co-supervisor of Mr. Mason from University of Huang and Dr. Atira from University of East London. And team members is me, Ahmad Omar Ahmad, and Jihan. So basically, the outline of the presentation is to do introduction about the drones and its application. After that goes to the problem statements and objectives, followed by the literature review and also evaluation of the literature review and the analysis. After that, the method and result and discussion. Finally, the conclusion and the future work. So basically, drones are categorized into 5 main categories based on their weight, which is super heavy and medium and light and micro. In this design, our the platform we are using for the drone is the medium-sized drone. And for the drone applications, we have so many types of application for the drones, which can be used in the agriculture and rescue missions and application of the in the environmental protection as well. So basically, this research is to study the capability of the wireless power transfer in order to facilitate the charging for the drone. So basically, the wireless charging is consists of 2 main elements, which is the transmitter and the receiver. And the transmitter itself consists of a DC AC inverter and of course the transmitter coil. In the receiver side, it consists of the receiving coil and then connected to the AC to DC regulator and filtering. And after that, the power goes directly to the load, which in this case is the drone's battery. For the problem statement of this research is the drone flight is limited for only minutes, between 20 to 30 minutes, according to Rohan in 2019, after the battery is fully charged. This represents one of the obstacle because, for example, in agriculture or in delivery applications for the drone needs to fly for longer time than that. In order to solve this problem, wireless charging station can be placed in between the distance, so the drone does not need to go back to its base, so it can just go to the wireless charging station charge. After that, the other drones go to do the application for whatever purpose it is. And then once the other drone is fully charged, then can goes to fulfill the role for doing the its applications. But at the same time, when we comes to the wireless power transmission, we have to study the types of the wireless charging, and also one of the obstacles is the drones is equipped with the motors, and these motors is require high capacity batteries, which require stable power flow in the charging process when the input power is not stable due to unlinear power supply of the solar panels to support the charging process. One of the problem statement is drones performs a task during the flight time, and the charging time needs a data acquisition for charging characteristic analysis, such as the charging current and also charging process and voltage of the drone battery. So basically, the objectives of this research is to review the advantages and disadvantages of wireless power transfer methods, considering drones battery charging. And second is to do comparison of the wireless power transfer methods, especially on the drones battery charging. The third objective is to develop the development trend of the wireless power transfer methods on drones battery charging. The fourth objective is to perform analysis of the efficiency of the wireless power transfer model at different distance and also different loads. So basically, the wireless charging transfer consists of three main methods, which is capacitive and non-radiative methods. The non-radiative methods categorized into three techniques: inductive and magnetic resonant coupling, and hybrid inductive and capacitive. And for the radiative methods is consisting of laser microwave and radio microwaves. For the inductive wireless power transfer, it has the advantage that it can be applied in many applications, such as charging a battery, toothbrush, and industrial heater. But still, it has the disadvantage of sensitivity to displacement, and also it has low rate of transfer electric charge at a higher distance. For the capacitive wireless power transfer, it has the advantage of lower power loss and also less heat production and also less weight of the system. But still, it has the disadvantages of drawbacks at higher voltages, and also it requires frequency and field strengths compared to inductive wireless power transfer. Coupled magnetic resonant method is have the advantages of lower power losses. Still, it has drawbacks at higher voltage, and also it requires high frequency. Hybrid inductive and capacitive power transfer, it has many advantages compared to the previous methods mentioned, which is number one is a lower power losses, flexibility in coupling structure, and also the efficiency can reach up to 85% or 86%. For the laser microwave, it's some of the companies, they have tried to implement laser microwave to the wireless charging for the drones, but still it has so many limitations, which is number one is costly, and the second of all, it requires a strong directive transmitter antenna, and this type of laser microwave is harming the human body, so it's not really cannot be implemented in any area. And also the complication in the maintenance and efficiency alignment. So when we comes to the evaluation of the literature review and development trend, there is two main factors have to be into consideration, which is the power produced by the transmitter, and also the current is produced by the transmitter. These two equation is too essential to study and analyze the system of the wireless power transfer. So basically, we have this table representing all the methods and the types of the wireless power transfer. And it's compared the frequency range and transfer distance, and also the power transfer efficiency, and also its applications and capability for drones charging. So for example, we take the inductive, it has medium frequency range, and also it has low transfer distance, which means the transfer distance is the distance between the transmitter and the receiver. But still it has high power transfer efficiency at low distance. For the hybrid inductive and capacitive, it has medium frequency range and medium transfer distance between the transmitter and the receiver, and have high power transfer efficiency. We can jump to the laser microwave. We can see it have high frequency range, high transfer distance between the transmitter and the receiver, and also have high power transfer efficiency. Still is not suitable for this application of drones due to its limitations, cannot be implemented in any area, especially in urban areas, in cities and so on. So we go further on and we study the transmitter distance between the range between the transmitter and the receiver. So basically, for the wireless power transmission based charging technique, radiative methods, the range of the transmitter distance is between 0 centimeter to 10 centimeter, and the frequency range is between 13.5 megahertz to 100 megahertz. The transmission efficiency is medium. For the non-radiative methods, the transmission distance can start from 1 meter to 10 kilometer. The frequency range is from 13.5 megahertz to 500 megahertz. The transmission efficiency is high. So after we studied the type of and the methods of the wireless charging transfer, then we need IoT system to do the communication between the charging stations and the base, to control the charging and to do analysis on how much power consumption by the battery. So we choose LoRa communication in this research because the LoRa doesn't need any other communication channels, and also it does not require Wi-Fi, so it can be implemented in anywhere, especially for applications such as border security and applications as agriculture as well, where there is no internet coverage. And the LoRa system has the advantage of low power consumption, and it has long range, can reach up to 15 kilometers. Also, it has high security and also easy to play, and also at the same time it's low cost. One of the main disadvantages of the LoRa is that it cannot transfer heavy data, for example, pictures or videos. It's very difficult to transfer it using LoRa. But in our research, we are only transferring numbers, which is the readings of the voltage, reading of the currents, and give us the calculation. After we do the calculation, we get the power consumed by the battery. So it's the best suitable option for this application. And LoRa technology have many types of topologies. One of the most interesting topologies is the bus topology, which is easy for installation and the cost effective, also used in small networks, and also cable required is less compared to another network topology. But also in the bus topology, you have the disadvantages of if backbone breaks, then the whole network fails. We have the other type of the topologies is mesh topologies. This topology is costly compared to the bus topology, and also each node requires a further utilities cost to think about, and also maintenance needs are challenging with the mesh topology. So our method for this research was to design of the wireless charging station and then transmitter and receiver coils design, and then transmitter and receiver electronic circuit design, and also electronic circuit design of the regulator and balancer, and then study the alignment of the wireless power transfer. Then we go to the other side is the LoRa network. We study the advantages and disadvantages of the LoRa. And then we studied the possibility of implementing new topology, which is hybrid mesh and bus topology. So this is the overall design of the wireless power transfer, which is supplied by solar power. And then it goes to DC-DC converter. From DC-DC converter, we presented that we add supercapacitor into the system so it can smooth out the power coming from the solar panel. Whenever there is drop in the power coming from the solar panel, the supercapacitor can smooth out the power and stabilize the power, acting as a power storage in this system. Then the power goes to the transmitter. From the transmitter goes to the receiver, and then goes to the charging circuit. From the charging circuit to the drone's battery. Basically, the charging circuit and the battery will be connected together in the drone, along with the receiver side. So the flow chart of the charging process is first initialize of the drone, and after that the drone is up to the target altitude for whatever application is doing, and then straight the flight to the destination, and then did the drone arrive to the destination? If yes, then is the drone battery is less than 3.8? If the drone battery is less than 3.8, then the drone go to the drone find the nearest charging station and automate and start automating movement and start monitoring until the battery voltage is 3.9 volt. After that, approach to auto landing, charging platform, and auto landing. Once it's auto landing onto the station, then start the charging until the battery voltage is more than 4.1, and so on. So for the wireless power transmitter and receiver, these are the main equations, which is calculates the inductance, and also it calculates the radius of the radius of the coils itself, and the distance between each loop of the coil. And then one of the most important element in calculating in designing the transmitter and the receiver coils is the quality factor, which is calculated by the equation Q equal 1 over R. R is represent the internal resistance of the coil, and then L is the inductance of the coil, and C is the capacitance of the coil. So basically, we have proposed a wireless charging station with 4 transmitter and 1 receiver, as shown in the picture here. And this wireless charging station have the capability to be moved in the x-axis and in the y-axis along with the z-axis. So it can move in 3 directions to the alignment of the alignment between the transmitter and the receiver coil. This is the top view of the wireless charging station and the side view of it. For the LoRa network topology, we have chosen the mesh bus topology due to its capability, as we explained earlier in the literature review, that for the bus topology, once one node is broken, then it will cause failure in the whole network. That's why we use the hybrid mesh bus topology to implement into this research, and it worked very well, actually. So in the result and discussion in this research, we actually implemented different loads at different distance, and we studied the output power of the transmitter and the receiver, and we studied the efficiency between them. So at load of 20 ohms, When the distance is 0 mm, it gives us efficiency of 98%. But when we make the distance 5 and 10 and 15 mm, it gives us 0 efficiency. When we increase the load to 30 ohm, the efficiency varies between 94 to 97.9 between the distance 15 mm to 0 mm. When we increase the load to 35 ohm, the efficiency varies between 68 mm to 96.6. And for the load of 45 ohm, the efficiency also raised between 88% to 97%. For the ohm 50 ohm, load 50 ohm, the efficiency rises varies between 68 to 91%. So for the result, now we came to conclusion that is the best distance between the transmitter and the receiver is 5 mm at all of the loads, because we can see from the difference load, the 5 mm somehow shows stabilities at different loads. So that's why when we conducted the experimental, we choose the distance between the transmitter and the receiver to be 5 mm. As a conclusion for this research, for this study and analysis, using hybrid system of inductive wireless power transfer and capacitive wireless power transfer is the best option for implementing wireless power transfer for the drone's battery due to its high efficiency power transfer. And also adding supercapacitors to the charging circuits is essential to smooth out the flow of the current, and apply multiple transmitter antenna to the design to increase the power efficiency of the wireless power transfer system. And also for longer distance transmission, the LoRa network system has been proposed, and also it does not require any Wi-Fi coverage. So this is for future recommendation and this ongoing investigation. We can see the LoRa network nodes. This was done in UOW lab, and the experimental was successful. The data was transferred successfully. All right. And this video shows the indoor charging investigation, and the study is still ongoing under process. All right, for future recommendation, a hybrid thermoelectric and solar power panel can be installed with the charging system to increase the power efficiency and the power outcome coming from the solar panel. Also, one of the future recommendation is the technique of fast charging of the batteries can be researched and incorporated into the wireless charging solution, which will decrease the charging time, resulting in decreasing the total mission time of the drone. So the paper was presented in the International Conference on Green Technology, Computing and Intelligent Technology in Johor Bahru in 2023, and it was published in the lecture note of Electrical and Electronic Journal, which is the publisher by Springer. Any questions? Thank you for listening. If there is no questions, I will go to stop sharing. All right. Thank you very much, everyone.
Okay, good morning, everyone. Okay, it's time from my side here. So everyone, can you hear me?
Yes, good morning.
Okay, thank you. So Mason Chua from SOE, School of Engineering Departments. And today I would like to present with the research title called SolidWorks Best Topology Optimization for the Quarter Design and Development.
Sorry for interrupt. Excuse me. Your mic is mute.
Oh, sorry about that. Okay, let me restart to present it. Okay, now you can hear?
Yes, loud and clear.
Where I muted.
I think you almost from the beginning.
From the beginning.
Yeah. Thank
Okay,
you.
okay. So okay. Thank you for that. Okay. So I would like to present a research title today called SolidWorks, the best topology optimization for quarter design and development. And this works was published in IET Digital Library in the last year. Team member Pavindran, Ahmad Omar, Serakana, Professor and Dr. Yap. We look at this title. Let me introduce what is SolidWorks. Actually, it's one of the software. We can use this software to draw any mechanical parts or any 3D graphic. Okay. Then what is the topology optimization? Is one of the algorithm from this SolidWorks itself. It helps to remove those surface area which is not necessary. Let's look at this. This is a piece of mechanical part, right? After we draw this thing and we just use the features from this SolidWorks, and it's able to help us to study and analysis and also slowly remove. You can see here many surface area is already removed. No matter this type of design or this type of design, the strengths and the strength to support, all right, to support the things that we want, is still the same. It's still the same thing. Okay, we can see all this. So this thing we call topology optimizations, and we design it. After that, we develop it. So this is what we are going to do it through this software and this topology optimizations. Okay, introduction. We can see nowadays drones is very famous. Can use for faster delivery, shipping, mapping. Even can do the insurance claims also. Okay, yeah, event photography we can see nowadays outside. Agriculture a lot. Okay, and a movie making also a lot nowadays people use by using drone. But for the current that what we are focusing now is mostly focus on the parcel delivery and the agriculture. So we can see when the payload is getting more heavy and heavy, of course we can carry more heavy, which is a better because we can apply a lot of applications in the market or industry. Now, how the drone actually fly? Normally we use a single motor to generate the thrust. The thrust will generate the force so that can lift up the body of the drone. Let's say we have a single motor with a propeller. Okay, one of these actually it can generate a force of 300 grams. So it can carry 300 grams. Okay, if let's say we have 4 motor, it's about 1.2 kgs. Add propeller, add motors, we can generate about 2.4 kgs. Now, from the literature reviews, octoquarters that we need to use octoquarters and quadquarters. Quadquarters is only use 4 motors and 4 propellers. So if we octoquarter means that we use 8 propellers, which are making very scientifically more powerful than the quadquarter. Also, octoquarters can fly higher, move faster, and able to carry a heavier payloads. And now the good things are we have topology optimizations allows for the deductions of the materials. And so we don't need to worry that to assess the weight. So the weight actually we can minimize after we through the topology optimizations. So nowadays we can see that there are 3 types of drones: fixed wings, hybrid drone, and rotary wing. So we are choosing the rotary wing under the octoquarters design. So we would like to actually to make the current market 8 arms into 4 arms, right? So that we can save the other 4 arms of the material. So from these objectives, actually we design and simulate an octoquarter drone body, and then we optimizing it and the octoquarter drone body using these topology optimizations, and also evaluate the performance of the 3D printed for the purpose of the applications. So this is actually the initial layout that we use a SolidWorks to draw. For A is for the base design, cover design, and the arm design. After that, we need to do the setting from the SolidWorks for the simulation purpose. This is a hardware. This is a hardware that we need to use to install into the drone body. So in order the drone can fly, this is a hardware components that we needed. And also we need a 3D printer. 3D printer. This is the optimizations from the, we need to do the optimization simulations. And this is the final result. Okay, after we can see they remove the certain places of the surface areas. And we assembly all together. And this is the 3D view from the SolidWorks software. Then we convert this file into the STL file so that we can print it in the 3D printer. The result is which was like, this is the result of the from 8 arms into the 4 arms. To the conclusions, the drone was able to carry out a deductions total reduction of 30% from overall before the topology optimizations and after the topology optimizations. We also tested trial use PLA or ABS materials. The top cover we were able to reduce by 40%, which is 35 grams. The base 25%, which is 60 grams, and the drone arm by 36% of the deductions, 70 grams. The whole body actually the octoquarters drone using 8 motors able to lift up about 2.4 kgs, including everything. But the drone body come out with all the other components, and the overall of the weight of the drone is about 1 kg. So we still have remaining about 500 gram can carry for the puzzle. Okay, thank you. And I need a Q&A. Okay, thank you, Dr. Chang, Chun-Yi. Okay, if no any questions, I will pass to Dr. Go. Thank you.
Hi, morning. Thank you, Mason. Anna. So I'm the last presenter. So without any delay, I will start straight. Yeah, today I would like to present the, can you all see the sharing?
Can.
Can, thank you. So my research title is Design, Development and Experiment Analysis of Solar Panel Cleaning System. So this research actually presented in Gen City last year, Gen City Conference last year, and it is a collaboration project between Galactic and UOW Malaysia. Yeah, and this system is actually focused on building solar panel cleaning system, which is practical to be implemented in industry. Nowadays, many people has aware of the impact caused by climate change, such as the increase of temperature, flood, etc. So renewable energy is one of the solutions to address climate change and reduce greenhouse gas emission. Yeah. So by utilizing this renewable energy, such as solar, wind, hydro, it can decrease the reliance on the fuels, which cause a lot to this one greenhouse emission. And in Malaysia, we are actually, we have sunlight year-rounded. That's why solar is mostly chosen to be implemented. However, might be hydro is the best way for the solution, because solar, after we put a lot of solar panels, and then after a few years, I mean, when we don't know where to throw away the solar PV. So for Malaysia government actually promote a lot or actively promote renewable energy sources. And Malaysia aim to achieve 31% of our energy capacity from renewable sources by 2025. And achieve 40% in 2035. But where are we now? We are actually currently at 13.3% only, which means in order to achieve this, we're actually short of 17.7%. Yeah. So government actually promote a lot, and there is a scheme called Large Scale Solar Program from 2017 to 2020, and recently they opened it again. Yeah, so this program actually leading to widespread, means that a lot of people actually installing these solar panels, and they kind of like sell back the energy to government. So where they implement or install the solar panel is at the ground, rooftop, floating platform. However, after implementation of so many solar panels, we need to maintain it regularly. If we don't maintain it, actually it will not achieve the maximum efficiency at all time. Means that you install the solar panel already, but might be you only get 50% of the energy. So this project is to solve this problem. Environmental factors such as temperature, sunlight intensity, weather condition, dust on the surface of solar panel are heavily affecting the efficiency of the solar panel. As for sunlight intensity, temperature, weather condition, that is very difficult for us to control. But dust on the surface, we can do something about it. Now, the dust and dirt accumulated on the solar panel has reduced the amount of incident light hitting the panel. According to the research done by Kazim and Hussein, who are very well known, or their paper are cited with by many researchers, at least more than 200 or 150 citation, they found that the power drop due to dust and dirt on the panel vary from 3 to 25%. And this value is an average values that compile from the data gotten by different countries such as India, Iran, Egypt, China, Mexico, and so on. Yeah. So in Malaysia, yeah, it's about there as well. But imagine in Saudi Arabia, only 1 month after they install the solar panel, the efficiency of the solar panel actually dropped 50%. So this is very serious. This project aimed to develop a solar panel cleaning system to reduce the impact of dust and dirt on the solar panel to improve the efficiency of the solar panel. This is a project given by the industry, Galactic Company. So we are focusing on this one, providing the solution, cleaning the solar panel on the rooftop. The objective of the research consists of use suitable 3D design software to design solar panel cleaning system. Students actually use this one, the AutoCAD, to design the system and then fabricate solar panel cleaning system. Of course, this is required by the company industry. After testing, after evaluate it, they can sell this product and evaluate the system effectiveness at cleaning. Before a company propose this project to their client, to their customer, of course, some data of effectiveness of the system must have. Solar panel cleaning system. There are many types of solar panel cleaning system in the market. We can see here the 4 main solar panel cleaning system. Of course, there are also human. Look at the picture at the right side. Human cleaning. Of course, human cleaning is the most efficient, but then it costs a lot of, and especially the project, the solar panel is on the rooftop, so it is quite dangerous for the workers to climb up there. Now look at the electrodynamic display. Electrodynamic display is a type of cleaning system that they put a transparent coating with the para-electrode, generate the electricity, like the electrolysis, and then with this electric, it avoid the dust to stick at the surface of the PV, surface of the solar panel. Yeah, for super hydrophobic aircraft, the same concept, but for this one, there will be a layer of coating on top of on the solar panel. So this layer of coating avoiding the rain, avoiding the dust to stick on the solar panel. It is just like our car we spray something on the mirror, and then we can avoid the raindrops to stick at the window, stick at the glass. And then we have this one, waterless cleaning system. Cleaning system using brush without water. Then automated cleaning system. Automated cleaning system here is the one that we focus with using water, using the brush as well. Now, solar panel cleaning system, the summary, we have did some study, compare these 4 methods. And for the first one, the electrodynamic display where there is a transparent coating, and then it's kind of like electrolysis concept. It is fast solving the problem, yeah, no water needed, but it unable to remove wet mud. And since solar panel is generating electricity, but this one, for this method, they required high voltage electricity. Then they use back the electricity. So it's like kind of not so efficient. Then the second one, super hydrophobic aircraft. It is a coating on the glass or on the PV. Efficient, no need water as well. Unable to remove wet mud. Yeah, is the disadvantage, but the coating is very expensive. Now, waterless cleaning system using brush or blower. Yeah, no need water as well. And however, it may not remove all types of dirt. And we need to frequently maintain the brush, which also not chosen by Galactic company. So the last one is the one that we implemented in this research, automated cleaning system, yeah, using robotic concept, efficient, consistent, but however, maintenance needed, yeah. Now, by looking at the design, here the design focused on wheel-based system with a cylindrical cleaning brush and a water tank. So this water tank is a 4.8 liter water tank. System control over a local Wi-Fi network using GUI. The beauty of this system, many product of similar product in the market, but here we have added one extra item, which is GUI on the computer, where we can actually monitor the condition of this robot. So for this robot, there are 4 wheels. There is a brush here, and then there is a water tank here, and battery. Due to the requirement, because requirement from this one, Galactic, the Galactic company has actually required the student to keep the weight of the whole system around 50 kg only, 50 kg or less. Yeah, so we have 4.8 liter of water tank. Actually, it's not a lot. Now, for the design, we have 3 microcontroller here. The 3 microcontroller named ESP32. The master microcontroller here is actually communicating via Wi-Fi to the workstation. Workstation consists of the GUI that will display the condition of the entire robot, the cleaning robot. And then the second ESP32, the microcontroller, is to control the motor, the speed of the motor. And then the third one, the microcontroller slave 2, ESP32 slave 2, is to control the DC motor, which can control the direction of the robot. So there are two 12-lead acid batteries here connected in series. So the voltage can actually split into 3 levels, 5 volt, 12 volt, and 24 volt. 5 volt supply to the microcontroller, 12 volt to the DC motor, and then 24 volt to the BLDC motor. And the GUI looks like this. The GUI actually provide, the reading of whether the motor, the direction of the motor, the speed of the motor, and the water level. So once the water level is very low, then the motor will then, the robot will then move back to refill the water to the terminal. So this, we have the monitoring system here. And then how to test the efficiency, the objective 3 efficiency of this cleaning system. We use this one, acrylic panel embedded with LDR. LDR is to actually measure the light intensity. Yeah. And then the student deposit means that the student put 10 grams of soil per section on this panel. And before he put the soil, the dirt or dust on this panel, he actually measure first the LDR voltage, means that at the very clean situation, what is the reading. Then after that, he put the soil on it and then read the reading again and get the difference in percentage. Yeah. So for the unclean panel, it look like this. First pass means that the robot passed through one round. Wash one time, the first time washing, cleaning the panel. It looks like this, then second time, and then third time. Now, as you can see here, from the result, before cleaning, the reading actually dropped to 0.6, 0.5, 0.6. Means that the reading actually reduced by 40 to 50% of efficiency. Then after the first pass, after the first round of cleaning by the robot on the panel, it increased to 0.8. Then second pass 0.9 and third pass almost clean. And student actually put effort to draw it. I put compile the result in and show it in MATLAB. So you can see that the red one is the dirt. Yeah, for the first pass, the unclean surface, a lot of red color there. And then go to the right hand side, the first pass, the red color reduce. And then bottom, second pass, more blue. And the third pass is like yellow and blue and green. So result is getting better and better. So for a conclusion, actually, for this research, the students actually did some experiment using the robot with water and without water. So from the result, with water, of course, we can get a better cleaning, with the usage of water pump brush in cleaning, the system achieve final surface cleanness of 88.9%. Compared to the without water one, actually after the third pass also, it is just increased by around 25% only. Yeah, so the last result is actually 46% cleanness. Development of the solar cleaning system using brush and water has achieved substantial good result. Yeah, around 90% after the 3 pass cleaning. However, additional testing and design iteration are required to determine the most effective means for developing the solar panel cleaning. Here, we will hope that if, let's say, we have time and this project is going to improve again in the future development plan, we would like to reduce the timing, because when we clean the solar panel, the solar panel, the water tank, 4.8 liter, can only clean not a very big place. So one go and flow is actually 9 minutes only. If, let's say, we could be able to, build a bigger or a higher, a bigger tank, then we can actually the robot can clean a bigger area. That is better. Yeah. And also with this increase of the tank, which means the robot will be more heavier, and we might look into how to move the robot with a stronger motor. So that's all for the presentation. Any question? If no, then I think we can end this session, right? Encik Imran?
Yes. Any questions so far from the other participants? All right, so I think we can end it by now, if no one to ask. And anyone? I see someone typing just now. No?
So that's all for today. We can leave the room, right?
Yes. So thank you very much for the presenters for today, and as well as for the participants as well. Right. And I hope we can see on the next services seminar, which will be conducted in or on 7th of August, the last one. All right. Which is
Okay.
next week. All right. Thank you very much, guys.
See you.
Have a good day.
Bye.
Bye.